Again, thank you for joining us today. We're coming to you live from the National Renewable Energy Laboratory. We're going to talk today about resiliency and solar PV. A few housekeeping things before we get started. If you have any technical difficulties, feel free to contact us through the questions panel. You should see that on the right side of your screen in that sidebar. And we will be taking questions from the audience through that panel at the end of the webinar. So if you come across things that you want to delve deeper into or you have questions about, keep that in mind, and we'd be happy to answer those at the end of the webinar. All right, so with that, we're going to get started. First, we're going to hear from Jenny Heater, who has a few programmatic things for the PV Cities program.
Hi, everybody. Thanks for joining today. I know we have a busy week this week, but just wanted to remind folks of upcoming events. So tomorrow, hopefully, everybody is already registered for Module 3 office hours. If you haven't gone into Litmus and viewed Module 3, it is up and ready to go. So hopefully, folks will have some time to take a look at that module before tomorrow. But if not, please join us anyway, and we're happy to answer questions on the fly. So that's what's up for tomorrow. After that, in early April, April 4th, we'll have our System Advisor Model Training. This is going to be a live webinar, so there's no module to view in advance. We do encourage you to poke around in SAM and try it out, see what you can do, and figure out on your own, or just become a little bit more familiar with how the program works before joining the webinar. But no pre-work is required. So the registration is there as well. And then Module 4 will be coming in April. The office hours for that will be April 25th at this same time. So I'll send out a calendar invite for that as well, but make sure to get that on your calendar. So yeah, I think that's all I have on my side. Just want to make sure folks know what's coming up. And I will turn it over to Eliza Hotchkiss, who will be presenting the rest of the content today, and just encourage folks to submit their questions as we go along.
Great, thanks, Jenny. As Jenny mentioned, my name is Eliza Hotchkiss. I am in the Strategic Energy Analysis Center here at the National Renewable Energy Laboratory. And today's bonus module is on using solar PV for resilience. And as Jenny and Harrison both mentioned, if you do have any questions, please go ahead and submit them in the panel bar on the right side of your screen. At this point in the trainings, you should have covered a few modules so that you understand developing goals, identifying and screening sites, and conducting a detailed site evaluation. The reason it's important to cover the first 3 modules prior to this module is that we're starting the PV resilience module with the assumption that you already understand some of the solar basics. This bonus module is intended to take some of the renewable energy integration and sustainability goals that your city or county may have and take them just one step further. In this module, we will start with an overview of resilience, covering the definition of resilience for the purposes of this training, why it's important, and integrated planning to achieve resilience. We'll cover how to assess portfolios and understand load profiles, understand common mitigation measures, then discuss how PV systems can be designed to avoid disruptions and provide power during grid outages. Finally, we'll end with some best practices to illustrate where resilient PV systems are already being implemented across the country. And again, if you have questions as we go along, please feel free to ask them in the chat box, and we'll try to answer some questions at the end of the presentation. The contents of today's webinar is shown on the screen, and you can see where we are in the presentation because each section has an introductory slide. So as shown on the screen now, the highlighted yellow portion indicates that we will now be covering the definition of resilience, just to help you follow along. The word resilience is a really hot topic. If you look up the definition of resilience, you'll find hundreds of definitions from different sources. Definitions include words like anticipate, prepare, recover, adapt, withstand, and it becomes overwhelming very quickly. Presidential directives and executive orders, various federal agencies and organizations all have their own definitions of resilience. So we always start out these presentations by defining resilience because this is how we are using this working definition. To simplify resilience and to incorporate solutions like on-site solar PV, NREL has defined resilience to be the ability to anticipate, prepare for, and adapt to changing conditions, and withstand, respond to, and recover rapidly from disruptions through adaptable and holistic planning and technical solutions. So this module will go into the meaning of the definition, but we're focusing on the ability to continue to provide power within a building or a campus or a city through holistic design and technical solutions, which include on-site solar photovoltaics. In order to understand why we define resilience the way we do, it might be helpful to provide an overview of resilience to give it a little bit more context. If you attended the goal-setting webinar as part of this training program, you'll understand that setting goals is essential in any city or county planning process. Cities within the Rockefeller Foundation's 100 Resilient Cities program, such as the city of Boulder, Colorado, have set goals as part of their resilience framework. And while resilience in the 100 Resilient Cities program is used more broadly and incorporates sectors like health, well-being, and economics, we are covering just the energy sector in this training. Setting resilience goals to help guide projects or actions is critical to the success of a resilience program, and vice versa. If a city has already established goals, resilient PV systems may be helpful in achieving those goals. This slide was created by one of our coworkers in our site operations office to summarize the process that NREL took to analyze its own risks and vulnerabilities on our campus here in Colorado. And in all of our resilience planning, we incorporate a stakeholder-driven process to determine where there are threats and vulnerabilities by looking at potential impacts and then the probability of occurrence as a way to rank those risks. Once we've determined where there are threats and vulnerabilities and have scored them, we can determine cost-effective mitigation strategies that will reduce risk and enhance resilience. Weighing the consequences and their likelihood is one way to prioritize and discuss some potential resilience options and create potential strategies to mitigate those. Understanding threats, vulnerabilities, and mitigation options allows for setting goals, and it's important to know what you are planning to become resilient to and for how long. This will help determine the type of system that can help meet those goals and the policies or financial mechanisms that can help with the implementation phase. So again, this graphic is a city example, but it could apply to a county or a regional situation as well. It's critical to remember that resilience cannot be achieved in a silo. So if you're addressing any one piece of a city or a county's challenges, you're not going to expand resilience as a whole. Hardening or improving one part of a system is not going to ensure resilience. It's going to focus on one piece. So we often take an integrated planning approach. Solving multiple problems with limited government resources can be helpful to implementing projects and achieving goals in a number of areas. So looking across your portfolio to see how some of these projects can be combined might ensure a more successful project. Energy resilience is one goal a city or county may wish to set and achieve. And in this section, we're going into greater detail around energy resilience specifically before diving into how resilience can be incorporated into solar PV projects. Energy resilience can only be achieved by understanding energy needs and targeting specific areas. It's important to understand load profiles and critical loads of buildings. And if you know that your climate zone means more energy is used on air conditioning in the summer months, then identifying how different facilities use energy can help when creating systems that are appropriate for specific buildings and the critical loads within those buildings. As an example, an office building with a data center is going to have a load profile throughout the year that's very different from a hospital. Hospitals need purified air to circulate in patient wards and operating rooms, as well as specialized electrical equipment to monitor patients. They also use a lot of hot water and have sterilization processes. So these loads are going to be different from an office building, which means there are different opportunities from incorporating energy efficiency measures to reduce those loads before renewable energy is installed, and then utilizing different types of renewable energy technologies. We usually recommend that energy efficiency be incorporated before renewable energy projects are incorporated because the systems are potentially more cost-effective with that approach. Another key piece to energy resilience is understanding generation, transmission, and distribution. We don't expect everyone to become an electrical engineer or understand the complexities of our modern grid systems. However, it is helpful to know a bit about generation, transmission, and distribution when we're discussing energy resilience. Most U.S. buildings receive power through a grid connection, and the power is generated in various ways in a power plant, typically using conventional power such as coal power, natural gas, or it could be large hydropower depending on where in the country the system is located. When power is being generated, it's sent to a transformer, as you can see on the screen here, to step up the voltages for transportation on the transmission lines. The higher the voltage, the lower the line losses, so utilities are generally ramping voltages up to make the network more efficient. When the power is needed at a building, the voltage is stepped down, again with a transformer, and then transported over distribution lines to a building where it's used at a safer, lower voltage. The energy resilient system that will make the most sense in your area will most likely depend on the type of grid system that you have and what some of those common points of failures might be within the system. Which brings us to the third piece of energy resilience, which is understanding common causes of its disruption. It's important to understand the common causes of disruption to your power system because that will help you understand how to create a more resilient system if you're utilizing PV and battery storage. If you live in an area where ice storms are prevalent or hurricanes occur with high winds, you know that power outages are seasonal. And if you live in an area with an older grid where the infrastructure is weakening and needs to be replaced or updated, the outages may occur more frequently but be less predictable. Understanding what causes power outages can be helpful in predicting when you need additional resilience or how to incorporate those into your projects. Here at the lab, we also work a lot on mitigation measures for grid resilience, and they depend on the vulnerabilities and the threats specifically. On the screen, you see a number of different mitigation measures from undergrounding critical lines, which could be cost-effective in certain areas along coastlines where you have hurricane threats or in tornado-prone areas, but might not make the most sense in other locations because of the high cost. Demand-side energy efficiency or demand-side management, diversifying generation, deploying distributed generation from distributed PV or microgrids, incorporating energy storage solutions, and then smart grids are all different mitigation measures that we work on, as well as the Department of Energy and a number of different national labs. So it really does depend on what the solutions might be for your specific area. But one that we are going to talk about today is the distributed PV and energy storage solution component. Which brings us to solar PV and resilience. This image may be familiar to all of you. It's a photograph of Manhattan during Hurricane Sandy, where entire New York neighborhoods lost power during the storm, and they lost power for weeks after the storm. Millions of people were left without power due to grid systems being out of commission. Sandy caused about $65 billion in damages in the United States, making it the second costliest weather disaster in American history behind Hurricane Katrina. And obviously, it's still early in collecting data related to the 2017 Atlantic hurricane season, but this figure may still be true. One thing that's important to remember is that states and communities along the eastern seaboard were impacted by Hurricane Sandy, including New Jersey. And it's interesting that when Sandy hit the East Coast, New Jersey had a lot of PV installed, as well as some wind turbines. And a lot of those on-site renewable energy technologies did not operate during those grid outages. And the reason is that there weren't interconnection agreements or islanding controls or battery storage technologies incorporated into these systems. So even though these two wastewater treatment facilities that you see on the screen had on-site renewable energy technologies, they were not able to operate during the storm. We might not think that's such a big deal, but the state of New Jersey estimates that between 3 and 5 billion gallons of effluent were discharged into New Jersey's waterways as a result of wastewater treatment facilities being without power. With no power, the pumps could not operate. And so this exposes some of the vulnerabilities that exist within our own infrastructure and opportunities for improving those. You may all recognize this slide from a previous training module, and I just wanted to illustrate that this really takes into consideration the generation, transmission, and distribution side, but focuses a lot on the end use side. And it's important to remember that a number of technologies and strategies can be deployed to enhance resilience. As mentioned previously, these include microgrids, demand response, energy efficiency, using distributed energy resources such as PV panels on rooftops, electric vehicles, and distributed energy storage technologies. All of these components can enhance resilience, but what's needed for distributed energy resources and storage to be resilient are those islanding controls and the right types of interconnection agreements with the utilities. To take this further, this is a schematic showing what a direct current PV grid type system looks like with battery backup compared to an alternating current system. Grid-connected PV plus storage systems are used to first meet a customer's load and then export excess PV generation to the grid in a grid-connected situation. This requires, obviously, an interconnection agreement and a net meter, but allows customers to sell energy back to the grid to help with the return on investment of a PV system. When wired for backup power, it is common to install a critical load subpanel and use PV plus energy storage systems, like a battery bank shown on the screen, to provide power to essential loads. These critical loads or essential loads could include refrigeration, essential lighting, pumps, specialized equipment in hospitals, just to name a few examples. And if this system is configured correctly, it can provide power to those systems during a grid outage. This slide is showing an example of an analysis that NREL staff conducted a few years ago to analyze the benefits of combining a PV system and a battery bank with a conventional diesel generator for a campus. The results were that the PV and battery system had a comparable life cycle cost to a generator, as you can see in the base case, the lowest cost solution, and the proposed system scenarios in the chart. But it helped to extend the probability of having power from 7 and 8 days to 14 days, as you can see in the graph at the bottom. The reason for this extension in survivability of an outage is that the PV and battery system are able to extend the useful lifetime of the diesel fuel, using solar energy when it's available to store it in the battery system, and then reducing the need to use the diesel fuel for the total duration of the outage in those first 7 days of an outage can be really beneficial. So this is taking a conventional system, a diesel system, and combining PV and battery just to show what the survivability might look like. The costs of the islanding technology and the battery storage are things that people often analyze when they're considering these resilient systems. And as mentioned on the previous slide, the cost can be comparable to a conventional system. NREL staff have researched how resilience can be valued and are finding that the net present value with resilience valued can nearly double the net present value, or the difference between the costs and benefits. So this may be one example of where additional equipment, battery banks and islanding controls with dynamic inverters could be justified, but the predicted outage frequency and the duration may impact that return on investment. Financial benefits and resilience benefits may be one way to prioritize projects based on the loads to be served or the criticality of those loads and the best technical options. Another way to look at the value of resilience is the value of lost load. So what are the costs if you don't have a resilient system in place? And then the last thing we want is for an investment to be made and for siting of these systems to not be considered. We want to prevent systems from being destroyed during extreme weather events or from malicious human attacks because these systems can provide power when the grid is down. So preventing situations like you're seeing on the screen now is really important. So also considering where these systems are being sited so that they can withstand natural hazards and be physically resilient is important. And as you see on the screen, some key points for siting are to make sure that the torque bolts are bolted to specification, that the PV panels are not with an overhang or roof or wall parapets to prevent uplift. Using appropriate installation techniques and the right types of materials is going to be really helpful. But then often finding a protected site is going to be beneficial as well. We want these systems to continue to operate when the grid is down and provide that resilient power as needed. To summarize, resilient PV systems will incorporate on-site generation that is sized for optimum performance or critical loads. They will include islanding controls and energy storage, like a battery bank, and will be sited to ensure minimal damage during severe weather events or just for general protection. Procurement and financing options could be incorporated that accommodate the value of resilience as well, and so these are factors that are being considered and could vary site by site. The next section that we'll be covering is on some best practices where solar PV has been incorporated for resilience goals or achieving those goals. These slides will be available to you after today's presentation, and you can access the examples of success stories that are shown on the slide by clicking on the links in the slides that you will have access to. But a few different examples of where solar PV has been incorporated include Florida, which has a SunSmart Schools and Emergency Shelter Program. This program was launched in 2009 and is still continuing as far as we know, with 115 schools having 10 kilowatt PV systems and battery storage incorporated. And from what we've learned, the schools have operated through recent hurricanes and other grid outages to provide that power to those schools. The Borrego Springs microgrid in California was launched in 2012, and it's a 26 megawatt PV system with two 1.8 megawatt batteries. This microgrid withstood 20-hour grid outages and has been a really interesting success story to keep an eye on. And the third example that's shown is the Stafford Hill, Vermont microgrid, which was constructed in 2015, and it has a 2.4 megawatt PV array with a 4 megawatt storage facility. The results are that it's had $200,000 in peak demand savings per year, which is helping with that return on investment that was mentioned previously. This provides emergency shelter services in times of grid outages and has been, again, another success story for the state of Vermont. Some building-specific examples are an apartment building in Brooklyn, New York was constructed a microgrid in 2015 with 400 kilowatts of PV installed 300 kilowatts of storage, and then also added a 40 kilowatt fuel cell for stationary power. And it provides 4-hour daily load reduction and resiliency during outages. So this is another interesting example. Again, New York has been pretty aggressive in terms of implementing microgrids after Hurricane Sandy so that they are preventing the grid outage scenario that they had when Hurricane Sandy occurred. And then Massachusetts has a $1.5 million grant for 14 different communities to establish resilient microgrid feasibility studies or conduct resilient microgrid feasibility studies. And so these will be interesting to keep an eye on as well. This was launched in February of 2018. Beyond the case studies and best practices, we do have a number of resources that may be useful to you as you're developing some of your goals for your city or trying to determine how PV can lead to resilience within your county. So these will, again, be available after today's presentation. Feel free to click around on this slide and see what kinds of resources are available. And then a video is available as well for Lions, Colorado, which is about 6 minutes, which may be of interest to some of you and give you some ideas about how to value resilience. And with that, I will pause there and see if there are any questions that have come into the panel.
All right. So just a reminder, if you do have a question for Eliza, feel free to submit it in the questions pane in the right-hand side of your screen. While they're working on that, I had one question. You showed those images of hurricane-damaged PV panels. I was wondering for people in regions that could be affected by hurricanes, if they follow those specifications that you listed, are there PV panels that can survive hurricane conditions? Installed properly?
Yeah, that's a really good question, Harrison. We are at NREL and at Lawrence Berkeley National Lab researching what the impacts were of hurricanes on PV systems. So it's a little too early to tell what the points of failure were. Typically, the panels are tested for static loads, not dynamic loads of wind and other pressures. And so what we're interested in looking at now is the array installation and how those racking systems or the panels themselves were installed and what some of the failures might have been.
Makes sense. All right. Let's see. Not seeing any other questions at the moment. I guess you gave a really good presentation. Just answered everybody's questions. We'll stick around for a few more minutes.
I've got a question too. Can you guys hear me?
Yes.
Yes.
Go ahead, Jenny.
Yeah, so I'm wondering, I know a lot of cities, have worked with their utilities to interconnect PV systems, but probably don't have familiarity with interconnecting storage systems, or maybe their utilities don't have, streamlined storage interconnection processes. Do you have any advice for our cities and counties about how they should be working with their utilities when they're thinking about installing a PV and storage system?
Yeah, that's a really good question, Jenny. I know that a lot of cities and counties are struggling with that component of resilience. The best advice that I can give on that is to continue to have an open dialogue with the utility to help them understand why energy storage is important to different facilities, like critical facilities such as hospitals or wastewater treatment facilities, police dispatch centers, to provide that reliable and long-term power that's needed for those systems to operate. There are a few different examples. I think if you look on the San Francisco website, they have a solar resilient PV tool. That might be a good example of where some cities have incorporated some of these projects to start to get some more ideas on how to have those conversations and what those policies or interconnection agreements look like with the energy storage component added on.
Okay, great, thanks. Another question for you is about best practices for if cities, maybe they already have PV on a building and they want to make the building more resilient versus trying to put a new resilient system on another building. How would you advise cities to consider, retrofitting buildings to be more resilient versus making new buildings resilient?
Again, that's a really good question. I think there's a lot to be learned from jurisdictions that have done this before, and the state of New Jersey incentivized modifications to existing PV systems after Hurricane Sandy. They have an energy resilience bank that provides rebates or incentives through, I believe it's a revolving loan fund, to help purchase things like dynamic inverters and battery systems for existing PV systems. So that might be a good place to look for ideas on how that could be incorporated. But it is possible to do to modify those existing systems so that they are a little more resilient.
Okay, great. Another question that just came in. This person, I believe, is at a municipal utility. So he says in the next year or two, they'll be creating a new municipal utility master plan. Do you have any recommendations on a template or planning toolkit for guiding implementation of microgrids, resiliency, etc.?
Yeah, we do have a few different examples. If you look at the microgrid ready fact sheet that is shown on the screen where it says best practices and resources, that might give you some ideas on how to incorporate some of those components. In terms of a template, there's nothing that I'm aware of that is in existence. I don't know if, Jenny, you have any ideas on templates or a toolkit for that specifically, but you might also look at the NREL resilience roadmap, because that is a process that was intended to guide resilience discussions at the stakeholder level. So if you are planning on getting a number of different stakeholders together to talk about what the new municipal utility master plan might look like, that could be a helpful tool. It does have some discussion questions and helps identify where those threats and vulnerabilities are within existing infrastructure and where resilience can be added in.
Okay, great. Yeah, this is Jenny. I'm not aware of anything else. So yeah, I would stick with what Eliza just covered. Next question is more just about market conditions. So when do you expect behind-the-meter residential storage will become more widely used?
That's a really good question. And it's a difficult one to answer because it really does depend on market adoption. I think it depends on the cost of those residential storage systems and whether or not there are incentives available. My guess would be that within the next 5 to 10 years, we're going to see an increase in the adoption of those systems. But that's just based on kind of what we've seen within PV adoption and the fact that I think resilience is becoming something that people are more aware of and they're willing to pay a little bit more for in certain areas where there are a number of grid outages or more frequent grid outages.
Yeah, and I can speak to that. Just one data point. I was at a conference last week and some of the major solar installers were talking about market penetration of residential PV and storage in California. And they mentioned that one company, I think it said, was 20% of their PV customers want storage in California. And the other company, it was about 60% of their residential PV customers wanted storage, both for economic value, because the rates in California are switching to a different time of use rate where it makes storage more favorable for the customer. But then they are seeing a lot of customers on the residential side, just for the novelty value. So there's still a lot of penetration, they think, for folks who, like the first folks who installed solar, they really just were into the technology and were willing to pay a little bit extra for something novel and new to support their residential use. So we have one more question that just came in. Is there a list of wastewater plants using solar?
There isn't a list that I'm aware of. We did have this question about a year ago raised by a city that we were working with. I can send some examples if that would be helpful after this, but I know that Camden, New Jersey has solar PV installed on their wastewater treatment facilities. And I know that a lot of wastewater treatment plants are using solar as a way to prevent evaporation. So there are a few different wastewater treatment plants that are using solar in New Jersey that I know of, but then also in California, a few are. So I can send a more detailed list at a later point if that's something that would be useful.
All right. I think that's all the questions we have for now. If anybody else has any last ones, send them in now. Otherwise, I think that will be it for our webinar today. Give everybody one more minute. All right, I think that's it. Thank you all for joining us. Just so you know, a recording of this webinar will be available online after we're done. So thanks again and have a great day.